So now we can measure the distances to objects inside the solar system using radar imaging, and we can measure the distances to objects within 100 light years using geometric parallax. But let's say that we want to measure the distance to a star that's even further than 100 light years. How could we do that? So this is going to be called spectroscopic parallax. Now, it doesn't have anything to do with parallax. They just call it that. But it has a lot to do with spectrums. So here's how we're going to do it. First, we're going to measure the distances to all the stars that are within 100 light years of Earth using geometric parallax. All right, so now we know the distance r to all of these stars. Then the next thing we're going to do is we're going to attach to our telescope a photometer that can measure the apparent brightness of these stars. So the apparent brightness is the letter F. So that's how bright the star appears to be. Now we know that for all of these stars by attaching a photometer to our telescope. Okay, then the next thing that we're going to do is use the photometry law. So the photometry law is F is equal to L divided by 4 pi r squared, where r is the distance to that object. So now we can calculate the luminosity of all of these stars. Okay, still isn't helping us yet, but we're going to get to it. The next thing we're going to do is attach to our telescope a diffraction grating. So a diffraction grating looks like this, and it has these lines scratched onto it. When light passes through the diffraction grating, it's diffracted. It spreads out into the rainbow of colors. So that for every one of these stars up here, we're going to look at their black body spectrum. So here's the black body spectrum. It's going to have the brightness going up and down, and then going sideways is going to be the wavelength of that particular star. And it's always going to have a black body spectrum that goes with it. And there's always, though, going to be one color that is going to be brighter than the other colors. And that's called the maximum wavelength. So this would be lambda maximum. And then, back in unit number 1, we had the black body radiation laws. And so one of them was called Wien's law. And Wien's law said that the maximum, sorry about the noise, the maximum wavelength is 0.0029 divided by t. So that if you know the maximum wavelength from this, you can calculate the temperature of the star. All right, now how's that going to help us? So the goal is, now that we've got the temperature and we've got the brightness, we're going to plot those on a piece of paper and make an HR diagram. So that's that lower picture there. So do you remember the HR diagram when we talked about stars? And we said it had the main sequence where stars that are living on are going to be plotted. So if we know their temperature and their luminosity, we can plot it on an HR diagram. So now we've got the HR diagram. That was the whole goal. Get the HR diagram. Okay, now what can we do with that? So the next thing is, now we're going to look at an unknown star that is located further away than 100 light years. So now we're concentrating on other stars that are further away. So we can measure their apparent brightness F using the photometer. And we can, using the diffraction grating, we can get their black bodies, we can find their maximum wavelengths, and then we can get their temperatures. So now we've got their apparent brightness and we've got their temperatures. Now take the temperature and use your HR diagram. So find the temperature of the unknown star, bounce it off the HR diagram, and find out the real brightness of the star L. And then once you've got that, we're going to go back to the photometry law, because now we've got this from the photometer, we got this from the HR diagram, and then we can solve it for the letter R. And now we can figure out the distance all the way out to 10,000 light years. Now this would still be inside the Milky Way galaxy, but now we've just extended our ability to measure distances all the way out to 10,000 light years. All right, so here's a sample question, if you can read it. You measured the apparent brightness of a star, and it is 4.21 times 10 to the negative 12th watts per meter squared. And it has a maximum wavelength of 3.63 times 10 to the negative 7th meters. How far away is the star? So you're going to write down what you're given and what you're looking for. So your first step is put that in there. Now, we know what the maximum wavelength is because we used our diffraction grating. So calculate the temperature. And it turns out the temperature of this star was 8,000 Kelvin. Okay, now find it, get out your HR diagram, find 8,000 down at the bottom, bounce it off the main sequence, and then write down what is the brightness of that star, which it turns out to be 10 times the brightness of the sun. Then take those two pieces of information, the actual brightness and the apparent brightness, put it into the photometry equation, and then solve it for the letter R. And it turns out that this particular star was located 900 light years away from Earth. So that's how you do it. Now, what's the problem with this particular technique? Okay, so if we go back up to here, this method is not useful for distances greater than 10,000 light years because the star would be too faint in order to figure out what its spectrum is. So the light would be too faint to pass through the diffraction grating and then to get its spectrum. So that means if we want to go further than 10,000 light years, we're going to have to use another technique. And that is going to turn out to be Cepheid variables, which we'll talk about in just a moment.